Okay, so welcome back students. So this is the last subtopic of the second module. So we have so far gone through the powder introduction, powder characterization, powder manufacturing, and in the last few lectures we looked at powder consolidation and powder compaction. Now the last stage, which is sintering, which is the most important and vital step in the powder processing, is what we will discuss today. The theory, the fundamental behind sintering. So basically if you look at just the method or what is happening in sintering is not very difficult to understand. The particles are coalescing together. So what is sintering? Sintering is actually this coalescence of particles, and densification is not a necessary requirement. Densification may or may not occur. So sintering does not always mean that we are talking about densification, although in the plots that you see there is a density plot versus time, and there you see that sintering is that the densification is occurring when sintering proceeds. But densification is not a necessary requirement. It depends on the configuration and the condition. We will see, for example, if you have two particles and they are in very close contact to each other. Now the mass can flow and get deposited over here, but the center of gravity of the two particular particles, they may remain constant and they may not change. In that case, densification is not occurring, and the overall shape of the particle has changed because of this sintering process, but the particle center to center distance has not reduced. So we will say that densification has not occurred. On the other hand, if masses or the mass moves from the inside of the material to the neck region and finally it reduces the center to center distance, then we will say densification has also occurred. So sintering, when we say what is sintering, remember sintering is coalescence of particle. Densification may or may not occur. Effectively, it is the joining of particles. There are two main classes of sintering. One is liquid phase sintering, meaning where one phase is liquid or in amorphous phase, and the second is the solid state sintering. Here both or all the phases, not both actually, you can have only single particulates or you can have more than one kind of particulates. Whatever it is, it should be in crystalline or polycrystalline phases. For example, take an example of mercury droplets. In the thermometers, old thermometers, you used to have mercury, and if sometimes you have broken it, you would have played around with it. So there you remember, if you have couple of droplets, you bring them close together and they suddenly squeeze and form one big droplet. So what was the driving force? Think about it. Why would they want to coalesce? Why was it magnetic or some other force that was driving them together? And does this coalescence imply densification? So in this case, would you say it is densifying? So again, you will have to look at the center to center distance between the two original particulates and see if the average center to center distance has been reduced. If not, then there is no densification. If it has reduced, then densification has occurred along with coalescence. Why does this coalescence take place? The main driving force is surface tension. For example, even one droplet you have, how is it able to hold on to it? So just remember a dropper, and you allow one liquid droplet to come out of it, and it hangs to it as long as it is not very large in size. If you have a droplet hanging from a dropper, that one piece of droplet will keep hanging. Why is that happening? That is because there is surface tension, something called as surface tension. So what is the surface tension? We will look at it in a moment. But that is the driving principle that ensures that there is, or that is what causes the densification of these materials. Now that we know what is the driving force, what about the underlying mechanism? You remember that thermodynamics is one aspect, but that does not ensure that that something will actually take place, because there also has to be some mechanism, some kinetics. So what is the mechanism? What is the kinetics behind this? That is something that we need to understand. Now let us look at the second slide, which is mechanism of mass transport. So here we discuss what are some of the possible mechanisms by which this mass transportation takes place and because of which sintering takes place. One of the most important ones is evaporation and condensation. So in all these examples, just remember you have two particles, and this is something like this. In fact, let me draw it for you to be able to visualize, although we will see lot of these diagrams later on. But when we are talking about sintering, it is good to have this in mind. We are in general we will start with sintering of two particulates, and this is the same principle that will get extended when you have more than two particulates. So, let us say somewhere over here, when you want to coalesce, what is happening is that somewhere these two particles should combine and become one. This can happen by particulates or the material mass flow taking place by evaporation and condensation. So, evaporation and condensation, something from here will evaporate, and then where should it condense? We want to coalesce the two particles. So, there should be growth in the neck, or basically neck should disappear, and therefore, it will get deposited over here. And similarly, for other mechanisms or other kinetics that we discuss over here, for example, diffusion. We know that several kinds of diffusion, or basically several paths to diffusion exist, and in the case of particulate coalescence, the important ones are surface, grain boundary and lattice. Such diffusion can take place through surface, it can take place through grain boundary, and it can take place through lattice. All of them in the end should somehow, or would in fact somehow allow the mass transport to move from one particle to basically the neck region. Once the material gets deposited at the neck region and this process goes on, slowly there will be no neck, and in the end you would not be able to say even if there were two different particles, you would see almost one particulate, unless there is a grain boundary getting formed over there. Then there is plastic flow. Again, this surface tension is it can cause compressive stresses. So, there are again these two particles you see over here, and because of the diameter that exists over here and over here, there may be compressive stresses generated, and because whenever there is compressive stresses generated, you can imagine there will be some deformation, only if the deformation or the stresses are very high, of course, but let us say the stresses are high enough. So, when the stresses are high enough, it can cause plastic deformation at some level, and those plastic deformation will cause plastic flow of the material to again the neck region. Similarly, there can be viscous flow. Because of high temperature, the material will act like a viscous liquid, and so material will flow again to the neck region, and the two particles will lose their individual identity and become one particle. In all these, you can say surface tension is the driving force for all these kinetics. However, which particular process dominates depends on the configuration and the particular process or the material that you are looking at, or the particular temperature. So, not only the material, process parameter, all those things will make a difference and determine which of these mechanisms will actually dominate. However, these are the main mechanisms for mass transport. So, the overall idea is mass should get transported. However, again let me emphasize that if the mass is, so this is your center of the two particles. Now, if this center to center distance remains constant, so let us say I make up in the end I get something like, let me use a different chalk over here. So, mass has moved from over here to here, but the center of gravity of the two particles remains same. So, in this case coalescence has taken place, it is no more two different particles, but the densification has not occurred. On the other hand, let us say it becomes something like this. So, you can say somewhere over here, and there may be a small amount of grooving that we will discuss. So, the center to center distance in the second case has reduced, and so you can say that densification has also occurred in this particular case. So, we see that surface tension can be described as the driving force for most of these phenomena. So, we will look at some of these particular mechanisms and see what exactly is happening at the particle level. So, for example, surface tension is a force per unit length. We know for a droplet, we can imagine what will be, we have the equation of what is the surface tension for a small droplet, and from there we will see that we can also derive relation for the surface tension that leads to compressive forces and hence a plastic flow. So, let us get down to some equations over here. So, we will start with what is the surface tension for a bubble. For a bubble, we know the surface tension denoted by sigma is given by 2 gamma by r, where r is the radius and gamma is the surface energy. Now, if we are not talking about a simple bubble, but a complex surface where 2 different diameters exist. In a bubble, the 2 diameters, the perpendicular diameters are equal, and therefore, you get a much more simpler equation. But if you have a complex surface like the neck over there, then there are 2 different diameters, and then for more general case, we have and what are these R1 and R2? These are 2 perpendicular radius for that particular point where you are trying to find the surface tension. So, over there you will find the radius of curvature in 2 perpendicular directions, and that will define the surface tension like this. So, in a much more complex shape, you can have only 2 different radius in the perpendicular directions, and here this is how you will get. Again, gamma is the surface energy, R1 and R2 are the 2 radii. Now, we will again go back to our particulates. So, over there, let us say let me redraw it over here for sake of completion. So, let us say this is something like this, what has happened, and this is the neck that has already formed. So, let us say this is the distance x after the neck has formed, and initially instead of radius here, just the way the convention is followed, I will follow the same conventions, and let us say this is the diameter, and we are assuming similar diameter for the 2 particles. So, this is the 2 diameter d, this is the x, and if we are looking at this region, there is a radius of curvature in this small area also. So, we are looking at the very neck region, at the very point where neck is formed, there is a small radius over there. So, it will look, in fact, if you were to look at it, and it has been found that this radius neck, let us say R subscript n. So, R subscript n is usually given by x square by 4d, meaning larger your particle size, smaller is this neck radius, larger is the x, smaller is the radius. So, this basically x also represents the growth of neck. If it is large, meaning your particles have coalesced to much larger extent, and therefore, radius of curvature would be much smaller, the radius of curvature over here. Now, let us put that over here, and what is the sigma that we will get? Okay, so here what we will have to do, you see this radius is convex in shape and this radius is concave in shape. That would mean that we will have to put a different sign for this. So, although I am putting a plus sign, so in here we will get a minus 4d by x square is equal to gamma times 2 over d minus 4d by x square. In comparison, let us see what will be the surface tension at some other point far away from the neck over here. So, let me call this sigma 1 and let me call this sigma 2. So, over here let us see what will be the equation for sigma 1, which will be equal to our same old equation, but with R1 equal to d by 2. So, this becomes gamma 2 by d plus 2 by d, because we are looking at this particular region where both the diameter, perpendicular diameters radius are basically the radius of the particle. So, this will be like this, which will be 4 gamma by d. Now, at this point let us take some typical values. So, let us say we have particle size d equal to 10 micrometer, and neck dia, or basically x, let us say x is equal to 2 micrometer. So, we are saying this is 2 micrometer and this diameter is 10 micrometer, and gamma, let us take gamma equal to some what value should we take, let it be some 1 megapascal per, so it will be per meter, because surface tension is per unit length. So, this will be not megapascal, it will be mega Newton per meter. So, when you divide it by this by so this is surface energy divided by d, will get the surface tension. So, let us say we have over here megapascal times meter actually. So, this will be 1 megapascal times meter, that is our surface energy. If you put these values, what is the sigma 1 and sigma 2 you would get? You would get sigma 1 of the order of and sigma 2 of the order of minus 9.8 megapascal. Why are we trying to do all this calculation? It becomes clear when you look at the relation or the relative values. What is the sigma 1 value? It is a comparatively very small number, 0.4 megapascal. What is the sigma 2 value? You see two things. One, it is in magnitude very large and it is negative. So, there is a compressive stress that is going on over here. So, in this particular neck region you would see some compressive stresses, and that compressive stress is very large, and the magnitude as you see is very large. That would mean that there will be large plastic flow. So, what we will get over here is what we were trying to, we wanted to derive for this kinetics, which is plastic flow. So, this is what we wanted to emphasize, that because of the surface tension you will have plastic flow, and therefore, material will flow from near the neck region into this region. And another thing is that there is a big gradient from here to over here. So, it is this gradient that is driving the material from over here into the neck region. Now, if you had x equal to x much larger, let us say if you increase x 2 times, then radius and the radius of curvature of the neck would increase 4 times, which would mean that this value would become much smaller. If this becomes much smaller, that would mean that you will have less compressive stresses. So, again what it is saying, that as your neck grows, the driving force decreases, the total amount of compressive stress that is acting, or the total gradient, the stress gradient that exists over here will reduce as the neck grows. So, that is one thing that we understand from this. Second is, when you have particle size which is smaller, so for smaller particle size the compressive stresses would be much larger. For larger particle size, compressive stresses would be smaller. So, again that you can obtain that from this relation. So, we have 2 things, like I said. One, that that for larger particle size you have smaller compressive stresses, and second, that when the neck is smaller in size, you have larger growth. So, these are the two things that we are able to understand from this particular equation. So, this is one of the mechanisms for the particle coalescence or the mechanism of sintering. Now, let us look at still another process. This time we will look at evaporation condensation. So, evaporation condensation is what? When the material is getting evaporated from one region and getting condensed into another region. So, let me draw a simple, basically what I am trying to show over here, how the radius curvature difference will lead to evaporation at one region and condensation at another region. So, what we will draw is a typical plot where you have r equal to positive. So, this is a positive radius of curvature, r is equal to infinity, and over here you have a negative radius of curvature. So, let me write it as positive radius of curvature. So, what is their implication? Now, when you have r greater than 0, then sigma is also actually proportional to radius, and with that we can say that delta sigma will also be positive. In fact, we do not even need to look at the delta sigma, we can look at the more much better term, which is delta p over here, which is proportional to sigma, and sigma is, sorry, this should have been proportionality sign. So, this is your sigma is proportional to radius and delta p is proportional to sigma. Therefore, if your radius is positive, delta p will be positive. Over here we have delta p equal to 0, delta p is negative over here. We are looking at delta p with respect to a flat region. So, basically when we say delta p is positive, what we mean is that the partial pressure, if you look at the particles over here, they will have a higher partial pressure with respect to what you have in this flat region, and compared to much even higher compared to this negative radius of curvature. So, there is a much higher partial pressure over here. There is almost because we are comparing it with the flat region. So, here with respect to flat region, this delta p is equal to 0, and with respect to the flat region in the negative radius of curvature, you have negative, or the delta p is negative. So, delta p is lower than what you will see over here. So, this is we are comparing the delta p, which is the partial pressure with respect to the flat plane. And from here what you see, that if delta p is positive, it means the amount of that particular material is very large in a region just over this. In fact, we can forget about this region, we can just at this point it will be better if we just look at delta p, how the delta p varies with the radius. So, delta p is positive when you have positive radius, delta p is 0 because we are comparing it with the flat region, and delta p is negative when you have a negative radius of curvature. What would that mean? That would mean that material will have a tendency to flow from, or when it evaporates from over here. So, let me draw it from over here. It will also have a tendency to evaporate over here and then condense over here, evaporate here and then condense over here. Similarly, this is still negative compared to this. Therefore, again the particles will have tendency to flow or evaporate from this region and then condense over this region. So, this is the driving force behind your evaporation condensation, as you can see that delta p is what is driving this, and delta p is again related to the radius of curvature. So, we have positive radius of curvature, we have positive delta P which is higher partial pressure, here somewhat lower partial pressure, and here even lower partial pressure, and therefore, you get this evaporation condensation mechanism that we see over here. Now, similar argument can be applied when we are looking at the diffusion process. So, in here again when you have negative radius of curvature, so you have smaller delta mu compared to this region. Here you have positive radius of curvature, delta mu is nothing but chemical potential. So, the chemical potential is higher over here in these region and lower in this particular region. So, from diffusion we know what will happen. From diffusion we know that material will have the tendency to flow, or to use the more appropriate word, to diffuse from this region or all these regions where you have a higher higher chemical potential, flow into this region of smaller or lower chemical potential. So, this is the region where it will come and move towards this region, and this diffusion can be of different type. It can move through the surface, it can move through the grain boundaries, it can move through the lattice. So, there are several kinds of diffusion that can take place, and the one where you have lattice diffusion taking place, particularly from the center or from the inside of the mass into the neck region, this is the one that will contribute most to the densification. So, this one is diffusion diffusion mechanism of mass transport. And you know that this will be temperature dependent. At higher temperature it will be faster. Diffusion mechanism of mass transport in sintering. So, we have seen three different mechanisms. One is the plastic flow, second is the evaporation condensation, and third is the diffusion mechanism of transport in sintering. And we see that all of them will contribute to coalescence of the particle by mass transport of material from other regions into the neck region. However, densification is limited to only certain particular cases, and that will depend from configuration to configuration. In one particular case we know that, for example, when diffusion is taking place from lattice into from inside the powder particles to the neck, at that point or in that particular case we will get lattice diffusion, and in that particular case we will get densification. So, we should not confuse that whenever sintering is taking place, densification will also take place. Densification and sintering may be independent. However, when we are looking at a much larger picture where you have the whole lot of particles, then over there no matter what kind of diffusion is taking, or no matter what mechanism is taking place, just because some pore regions in between are getting disappeared, the material will have the tendency to shrink, and so overall you will always get some amount of densification no matter what is the mode or mechanism of sintering. So, what we saw, let us get back to our slide. So, what we saw that these mass transport mechanisms lead to the formation of neck and its growth. We also saw that a small amount of vapor condensing, or in fact any other mechanism, where a small amount of neck is removed, a large amount of surface area, you just increase the neck size by small amount. So, initially you have just a point contact, and then you have a little bit additional amount of material over there. So, neck size is increased by just a small amount, but the surface area decreases by a very large fraction. So, that means that initially you will always have a much higher rate of sintering. Sintering is equal to neck growth. When the neck growth occurs, it is sintering, whether or not densification occur. And what is densification? It is particle center to center approach. However, I am also saying that in the overall big picture, when we look at much larger number of particles, the centering will always accompany with some amount of densification, even though if you look from the definition of center to center approach, there may not be densification. For densification to occur, mass must move from between particle centers to the neck region, which is what we saw when we had lattice diffusion taking place. Here are some more information about sintering rate. We said particle size will make a difference. We also said that what stage you are, it will also make a difference on what is the sintering rate. So, here we see one plot that describes this. So, on the y axis you have density, and again you see whenever we are talking about sintering rate, you would see that in the end we talk about density. So, densification is taking place at the macro scale. Only when we look at the definition of particle to particle distance, then we differentiate that all different kinds of mechanism of sintering will not lead to densification. But when we are looking at the big picture, when we are looking at the whole compact, then whenever you are doing sintering, there will be densification occurring, and that is why on the y axis you see over here we have density, percentage density, and on the x axis you have temperature. So, in this particular case, nickel particulates were heated at a rate of 6 degrees Celsius per minute, and 3 different sizes of nickel were taken: 0.05 micron, that is 50 nanometer, 5 micrometer and 50 micrometer. So, what you see at very lower temperature, the 50 nanometer nickel particulates start to densify, and it reaches very close to 100%. In fact, by the time it reaches 800. On the other hand, as you keep increasing the particle size, this amount of growth, that the growth takes place at a later temperature, something like here in the 5 micrometer, it is starting somewhere at 400 or 350, and by the time it reaches 800 degrees Celsius, it is only 65% densified, and for 50 micrometer region, it has not even started by the temperature of 600, and at 800 it is just 55% densification, close to 55% densification. So, when the particle size changes, densification starts earlier and it gets to completion and to a much larger saturation value. Another thing that you see over here is that at the initial stage, if we call this the initial stage, the densification or the rate of change of density with temperature is much larger, and with time it decreases. Again, that is related to neck growth. Here initial necks must have formed, most of the particles have initial necks. So, the neck radius is very small, and therefore, you see a much larger growth, and as the neck size becomes larger and larger, the growth rate or the sintering rate reduces. So, particle size makes a difference. What is the stage at which you are looking at, it makes a difference. Temperature makes a difference, and of course, what is the material, that will also make a difference. Here the same thing is explained in schematic. So, here is the neck size x over d. You remember x is the size of the neck, x is equal to 0, it means just the particles are in point contact. D is the diameter, and on the x axis you have the time. So, this for two different temperature, it is shown how the x over d is changing. So, for lower temperature you get lower x by d, for higher temperature you get higher x by d, that is one thing. Again, but what you see is that initial time period, the rate of change of x by d is large, and with time it gets saturated. So, again our concept that this rate is higher at initial stages is still holds true. Surface area reduction. So, now that was the most important driving force, surface area reduction. So, that is also shown here on the y axis, delta S by S naught. So, this is the amount of surface area that has changed, and this is the initial as the surface area, and again it is shown with time. So, at higher temperature it will reduce faster and reach to a much larger saturation value. At lower temperature it will reduce at a lower rate and reach a lower saturation value, and again we see that initial rate is higher than during the later stages. This is shrinkage. So, this is the more, you can say, appropriate or more easily measurable quantity when it comes to densification, the overall shrinkage between two particulates delta L by L naught, and again we see similar kind of behavior. And the final overall densification, if you will measure the density and then again measure it with as a function of time, this is the kind of plot that you will see. So, overall that we have seen that sintering rate depends on particle size. Smaller the particle size, higher the sintering rate. It depends on what stage you are. Initial rate is much higher. It depends on the temperature. Higher the temperature, higher is the sintering rate even in the initial stage, and you reach a much larger saturation value. So, sintering is faster during initial stages when neck curvature is very large. Now, again to re-emphasize the point about sintering versus densification, another plot is shown here. Here you are shown the two particulates. So, these were your two original particulates. Now, you see there is a small amount of overlap, and why is that overlap taking place? Because the center to center distance has come closer, and that center to center distance, as it defines, there are some of these mechanisms shown over here. So, and in the caption you can see that only mechanism 4, 5 and 6 cause densification. So, you see mechanism 4 is grain boundary diffusion. So, basically the particles are getting diffused into the neck region by grain boundary mechanism. In path 5, lattice diffusion, which is from over here, from somewhere over the center, the material is going to the neck region, and in path 6 you have lattice diffusion, which is from the center to somewhere in the neck region the material is flowing. So, some of these methods, like I said, will lead to densification, and again this densification we are talking about is center to center distance. Now, having talked about sintering and densification, let us say we sintered these two particles. So, we started with this. So, do you think after completion of sintering will it look like this? This is how it should look like. That is, you have the two particles now completely coalesced and there is a boundary in between these two. Is that the right concept? Well, let us look at it. We will look at the equation to be able to, not the equation, but just a simple schematic to understand if this is the right process, right figure to represent two coalesced images, sorry, the two coalesced particulates. So, what we are saying is we started with like this, so is this, the question is this a right representation or is this the right final stage for the two particulates? The answer is no. Why? We will see in a moment. Let us say we have something like this, and let me use. So, there is an interface over here which has energy, and there are two interfaces over here which also have energy. So, we can say that there will be energy, there has to be energy balance over here. Now, you see, if this were the configuration, these two would have been like this, and therefore, this energy is not getting balanced, which would only happen if there were no energy in this, but that is not true. There is some energy associated with grain boundary, and therefore, the actual surface must have a shape like this, and therefore, if we so let us call this angle psi e, and this is what is called as grooving, grain boundary grooving. So, if you heat, whenever you have polished a sample, the grain boundaries are exactly perpendicular to the surface, but if you allow or heat the sample just a little bit, the grooving is bound to occur, because the grain boundary energy must be balanced through the other two surface energies. And therefore, from the Young's equation, you can write, you can even find out what is the grain boundary energy if you know the surface volume energy of these two, of the surface to volume. So, this can be written as gamma SV cos So, gamma GB can be given in terms of gamma SV, and you can measure psi E experimentally, or in other words, you can, if you know grain boundary energy, you can calculate gamma SV, and if you know the psi E value, which you can measure easily. So, this is the psi E angle, and that would mean that the final shape should look like something like this. Even you are centering only two particles. Remember, we are talking about only two particles here over here, and therefore, and there will be a equilibrium psi E. So, no matter how long you center, this shape will be the final shape. It will not change beyond this if there were only two particles, and that means that if we have to look at so if we were to look at the total energy, we can write like this: gamma GB times area GB is for the two particulates. We are talking about gamma SV times surface of the particulates. So, this is the total area of grain boundary, and this is the energy, grain boundary energy per unit area. So, this is the total energy. Similarly, this is the surface volume per unit area, and this is the area of the surface. So, this will be the total energy, and if you were to plot this with psi E angle, you would get so there will be a minima, and this is the psi E that will be your equilibrium psi. So, this is the angle at which it will become equilibrated. In some other cases, if for example, if the material was different, you may get a different psi E. And what do these mean? So, let us say this is psi E1, this is psi 2. So, psi E1 is less than psi E2. It means that in here the neck growth is low neck growth. And in this one, large neck growth. So, this is how your plot will look like. The higher the psi E value, higher is the neck growth. Now, let us ask ourselves that here we have taken that the two particles are of same size. What if one of the particles is much smaller than the other one? So, let us say this time I have this plus a small particle. Now, if we follow the logic that we described earlier, we would get a equilibrium psi. So, this is some psi value, the equilibrium psi value. However, now note that the particle radius is smaller over here and particle radius is larger over here. So, the vapor pressure over here is much smaller and vapor pressure is much larger over here, and therefore, particles will the material will have the tendency to condense. I am sorry, the other way around, actually it is the vapor pressure is larger here, delta play larger, and here it is smaller. because at delta p when the radius becomes infinity, delta p is 0. So, smaller the radius, delta p is larger, and therefore, the particles here will evaporate and condense. So, eventually what will happen? You will have a larger particle, and this will be what we can call Ostwald ripening. So, in sintering you may even have particles growing, or basically larger grains forming from the smaller particles, from the combination of smaller and larger particles. Now, let us move ahead and let us again take a look. We have always been saying that in the neck region, just a small amount of addition of the mass will change the surface area by a large margin. Let us look at these two particles. These are in the liquid state. Now, when these two particles come together, you see a very small neck has formed. So, the amount of material that has gone over here is very small, but how much has the surface area reduced? Now, the overall surface area would initially have included the whole curvature, but now just a small amount of addition has reduced the surface area in both the spheres up to this length x. So, a large amount of surface area has been reduced, and slowly you see initially if you were to compare it with sintering, there is a very large sintering rate over here, and the neck is growing, x is growing even further by addition of small amount of particles at the neck region. And once this neck becomes large enough and the radius of curvature reduces, then the sintering rate reduces. So, that is how in general a neck growth takes place. Now, let us it is time for us to take a look at stages of sintering. Broadly, there are 3 stages of sintering. In the initial stage, you have neck and pore formation. So, the particles will stick to each other, they will form neck, and hence there will be a very large network of pores. In the intermediate stage, pore rounding, grain growth, and some densifications take place. So, you will have the pores which were now very large and interconnected all throughout, they will start to round off, they will become rounded in characteristics. Most of the property development of the material takes place during this stage, and in the final stage, where initially now in the end of second stage you had network of pores, cylindrical pores joining from here to there. In the final stage, sintering occurs with closed pores. So, now the cylindrical regions get closed, and only at the nodes you will have spherical pores remaining. Driving force is very reduced because of very little excess surface area, and hence the final stage sintering is slow. So, here the sintering becomes even slower because the overall driving force has reduced, surface area has reduced. If you were to look at the equation, it will look like this. In the initial stage growth, you will have x over d, x is the neck size, d is the diameter, and b is some constant which carries the process parameter. It also carries some of the material characteristics, and it will be given depending on what is the mechanism. So, the different mechanisms are described over here, and for them the n, which is the exponential factor over here, and m, which is the exponential factor over here, are given. So, for different mechanisms like viscous flow, plastic flow, evaporation, condensation, lattice diffusion, grain boundary diffusion, and so on, it is given over here along with definition of these different properties. Now, this B itself is actually a temperature dependent parameter. So, if you were to write it in terms of temperature, then it will look like this, where Q is the activation energy of the process through which this diffusion is, or this process is taking place, this densification is taking place, and here B naught will be your athermal quantity. This particular equation in general holds for values of x over d less than equal to 0.3. When the x over d value reaches 0.3, then we will say that initial stage growth has come to an end and we move on to the intermediate stage. So, but before we get over there, let us look at some more facts about initial stage growth. Surface tension equation allows estimation of the vapor pressure, flux diffusion and stresses. You can use surface tension equation that we saw for one of the cases and estimate the vapor pressure or flux diffusion and stresses. We saw an example of calculating compressive stresses. Sintering rate can be measured more easily in terms of shrinkage rather than neck size. So, neck size is a parameter which we use for densification, but that is not so easy to calculate. You will have to take very accurate micrographs. On the other hand, the parameter which is the interparticle distance, that can be much more easily calculated. For example, it start with you had L naught and after sintering the center to center distance is L naught minus delta L. So, this delta L represents the shrinkage in terms of distance to center distance. Shrinkage approach to monitoring sintering is valid only for bulk transport processes. Next we get to the intermediate stage and this is characterized by this kind of shape. So, there are grains, this is a grain or a particle which has stuck to the other particle and in between the particulates that it is attached to there will be network of pores. So, these are long cylindrical pores that are forming a network. In a much you can say simplified way, we can say it is a 14-sided tetrachiidecahedron grain in the much more ideal or simplified form. During this stage densification takes place by diffusion of vacancies away from pores. So, the vacancies move away from pores and get annihilated at the grain boundaries. So, this is what describes the intermediate stage and let me quickly write down the equation which describes this. So, this is fractional density after sintering, this is fractional density at the start of intermediate stage, meaning at the end of initial stage. Bi is a constant that varies inversely with grain size and Ti is again the time at the start of intermediate stage, meaning if you are calculating the time from the beginning, then Ti is the time at which initial stage ends and intermediate stage starts. So, at a particular time t, rho s would be given by this equation. Now, let us move on to the final stage. This stage is characterized by tetrachiidecahedron grains with spherical mono-sized spores at the corner. Now, in the previous stage we had long pores all around like a square, but here those regions have also been filled and you are only left with pores at the corner and these are now isolated pores. That is the characteristic of the final stage. During final stage sintering, the pores are closed, isolated and try to be spherical. Because of the surface energy term, they will try to reduce and that will happen when the best when it is spherical in shape. Pores can also grow by Ostwald type ripening. So, like the particle ripen by Ostwald ripening, similarly pores can also grow. If the pore has a trapped gas, now we are doing it in some atmosphere. So, inside this there is still some of that gas remaining inside this. So, that gas is now trapped inside. Then the gas slows or prevent pore elimination. Now, if that gas is remaining there, it will not escape. Now, it is closed, it is isolated. No matter how much pressure you apply, you cannot get rid of those gases. Hence, sintering is preferred in vacuum. If you want to get a very high density, get rid of all the pores, then you have to do the sintering in vacuum. The rate of pore elimination in the final stage depends on the balance between surface energy and pore gas pressure Pg. We will see at the equation in a moment. So, this describes that the rate of pore elimination will depend on the balance between surface energy and pore gas pressure. Equation shows that when gas is trapped in the pore, densification rate will go to 0 even before porosity is eliminated. We will see that in this particular case we will not be able to get rid of all the porosity. There is a possibility that porosity not just a possibility, in most of the cases if you are doing in some atmosphere, the pores will not be removed. Pores at grain boundaries or pores at lattice are more stable. So, you have to, this is a question that you should ask yourself, that which of them are more stable, which of these do not get eliminated, and I will give you an answer, but you must think about it. The pores in the lattice are more stable, that is they will not get eliminated. and pore has a very strong role to play. For example, in alumina, it is opaque. You have seen it is very opaque. It is white colored almost. It is mainly because of pores. Otherwise, alumina, which is Al2O3, it is transparent. So let's now that we have described the final stage, again let's describe the equation that describes this final stage. So if we were to look at d rho by dt, which is the rate of change in the fractional density, then it will be given by 12 dV, where dV is the volume diffusivity, omega is the atomic volume, k is the Boltzmann constant, T is the temperature, and G is the grain size, times 4 gamma, where gamma is the solid vapor surface energy, dP is the pore radius, minus Pg. Now the first thing and the most important thing that you will see here is that if you keep increasing the pressure, which is if you are doing it in a very large high pressure condition, sintering is being carried out at high pressure, then Pg will increase, keep increasing, and at certain point this whole quantity may reduce to 0. And what will happen when it reduces to 0? d rho by dt becomes 0, meaning there will be no more change in the density shrinkage. Shrinkage rate will not be will not move any further, and the density will remain constant at that point. Although dP may not be 0, dP may not be 0, meaning the pore diameter may still be some finite value and your rate of densification may come to 0. So that is what something can happen, or in particular, actually I should not say may happen, it does happen when you are doing in some atmosphere, because there is a pressure and that there is some gas that you have used, and that gas gets trapped inside those pores, and that because of that there is a pressure, and the pressure and the surface energy term, they balance each other, and therefore your densification may come to 0 even before dP, which is the particle pore size, it may come down to 0. So there is an example problem you should try, and you can discuss it with the TAs and try to solve it on your own. We will just summarize the 3 different stages of sintering. Initial, there is rapid interparticle neck growth, relative fraction density may reach up to 0.65, 2 mono-sized spheres in contact, this is our idealized model. In the intermediate, equilibrium pore shape will with continuous porosity. So you have network of porosity and your fractional density may reach 0.65 to 0.90, tetrachi-decahedron with cylindrical pores of same radius along the edges, pores are of that kind of form. In the final stage, equilibrium pore shape with isolated porosity are formed, and you may get fractional density greater than equal to 0.90. Tetrachi-decahedron grains again with spherical mono-sized spheres at the corner is the idealized form, idealized shape. So this is a schematic of what is happening in the different stages. You have loose powder, then you have initial stage where you have neck growing, and in the intermediate stage you have network of pores. So these are network, and in the final stage these are the pores at the corner of the grains. And these are some of the real micrographs that you see. So here you have copper spheres, and here at different stages. So at particular temperature, which is 1000 degrees Celsius, at different time you see like this, and even at the end you see some pores at even after 96 hours. So this is how it will look like. And we will end with this slide. Here again you have tungsten powder which has very high melting point, and you see that at the green density you get is 58%, which is very low, but at the end of the final stage of sintering at 1750 Celsius you still get some pores. So there are still large number of pores because the sintering temperature is relatively low for tungsten, which has very high melting point, and these are the different stages of sintering. So this covers the sintering concept that about the powder processing. So we have now looked at all the different stages of powder processing, starting from powder characterization to compaction to consolidation to compaction, and finally to the sintering. So sintering, like we said, is the most important and vital stage, and the understanding sintering theory is very important. you would if you have any doubts about this, or if you want any clarification, please do get in touch with us, and you can ask questions as usual to the TAs and to us, and we will answer as soon as possible. So, that brings us to the end of this course, and hope that you have had good opportunity to learn, and I wish you all the luck for your final examination. Thank you.